So our next speaker is Yiannis Aloimonos. He's a professor in computer science.
Thank you. It's a great pleasure to be in the Maryland Robotics Day. As you've seen, there's a lot of diversity of approaches in Maryland Robotics. Today, I will talk to you about a new topic on which we are working. We started working on it. We have given it hyperdimensional active perception. Now, this is joint work with Cornelia Vermeulen, who is here in the audience, one of the organizers of this workshop. In our lab right now, we have 3 funded projects in robotics. One is from Amazon on conversational robots for achieving manipulation tasks. You speak to the robots and they speak back to you, and you have a dialogue and you try to get them to perform actions. There is a project on underwater robotics for intelligent aquaculture involving many people. It's led by Miao Yu of mechanical engineering. And we are doing underwater computer vision for finding and counting oysters. And the last topic is on fusion perception and control. You know, perception and control are kept in separate spaces. They are also done by different people. Control people and the perception people. This balkanization exists also within perception, because the audio people and the perception people are also different. So that has created a problem, and it is not helpful in accelerating progress. Why? Because neuroscientists have been telling us for a long time that the representations of things that we have in our heads are sensorimotor representations. Sensory and motoric representations together in one signal. But roboticists have been ignoring this. And one of the difficulties that this causes is very difficult to do what we call active perception, where both the perception and the motion are fused into one thing. So what is the gist of the argument? Here is the argument. It's a computational argument. Now, the actions that we do, of course, I refer to humans, but in the back of your mind, you should have cognitive robots of the future. So the actions are really guided by prospective information, as opposed to instantaneous feedback. Because adaptive behavior has to deal with the fact that events precede feedback signals. In humans, the delays are about 250 milliseconds. Now, relying on feedback is not adaptive. The way to overcome this problem is to anticipate what is going to happen next and control behavior on that basis. So this notion that an intelligent system is a predictive system is taking hold in the community right now. And people are realizing that a very fundamental component of intelligence is to be able to predict. So if you want to predict, what are you going to predict? You will predict everything. You will predict the vision, you will predict the sound, you will predict the action, you will predict the smell. You predict all the sensory streams and the motor signals. How are you going to do that? Are you going to predict each one separately? What if you have errors as you do this prediction? How will you be able to make sure that everything is consistent. So the way out of this is to take all the signals, including the motor, and make a new signal out of them. That thing can happen through the use of hyperdimensional computing. This is why we call this framework hyperdimensional active perception. So, you know, in the past several years, we've been developing very small drones that can find gaps and holes and move. Now we are giving them legs so that they can get into rubble in a earthquake. Now, doing this quite some time, we realized that one of the difficulties, because we want to have as little as possible computation going on, because those are very small, tiny drops. They cannot carry too much information, too many sensors on them. Constraints or swap constraints. So we realized, would it be nice if instead of having this IMU information or information from images and control, wouldn't it be nice to have one signal? What? So when you think of robots, it's like cognitive robots, it's like, you know, they have a mind as well. And that mind is nothing but an amalgam of various capacities like perception, action, decision, knowledge, language. The problem is that each of these competencies is done by different communities. And the different fields, they speak different languages. That reminds you of the Tower of Babel story. People who were building a nice building, finds caravans, there were languages. And the building was never built. Hyperdimensional computing provides this new language. With hyperdimensional computing, all the operations inside the intelligence system acquire the same kind of ontology. That is, images, videos, sounds, photo sequences, smells, tactile information. All of these are represented with hyperdimensional vectors. What are hyperdimensional vectors? Vectors in very high dimension, in a vector space of very high dimension. We use about 10,000, but we don't know yet optimality, what is optimal. So the brain, as you know, computes with assemblies. Groups of cells that are excited or inhibited, and they are exciting other assemblies. So in some sense, the operation of an intelligence system amounts to transforming hyperdimensional vectors. So as I discussed, out of vision, sound, motor, you get one signal, and you use that signal to do prediction. Then you can unwrap it and get everything back, which you need in order to perform actions. So this field was developed 20 years ago, but the deep learning extravaganza made it difficult for people to notice it. Now there is a revolution that is, by the day, more and more people are realizing the power of this framework. So basically, you think of an intelligence system as a 10,000 dimensional hypercube. Vectors of zeros and ones. And these vectors represent everything: images, video, sounds, control, movements. So, very elementary, there are two basic operations. Addition, you can add those vectors, and you can also multiply those vectors. But multiplication can take various realizations, like convolution can be one. Score can be multiplication, or other operations as well. The addition gives you a vector which is close to the ones that you are adding. The multiplication gives you a vector which is far from the ones that you are multiplying. The multiplication is binding things to each other. Create one thing that has both of them inside. So you can imagine you have a video and you have a control signal, and if you would take the convolution of the video with the control signal, as my student Levi is doing, then get a new signal that has both of them inside. So these notions become feasible in hyperdimensional space, because you have these very two simple operations. And you can do AI, can build memories. And there are many ways of doing it, as you can see here, but the ones that we use are based on Canerva's hyperdimensional framework that utilizes vectors of zeros and ones and distance permutations in order to represent sequences. And you can represent sets with this and records of any kind. So we'd like to apply this theory to the ego motion problem. I would like to do it in a simple kind of way so that we can understand how to build up these kinds of operations. So this means that we have to bind the perception with the movement. Now, when you have images and you want to make hyperdimensional vectors, that's a hard problem. So, it is, but the problem is still unsolved. However, if you have event images, it becomes much easier. Now, for the ones who don't know, event sensors are like this one, that they are putting on the image point that represents an event. Sensors basically see the motion. The RGB sensors don't see the motion. You have to compute it, but those guys see the motion. And the nature of the images is such that it makes themselves naturally, applicable to the hyperdimensional vector construction. Okay. This effort with the DVS sensors is led by Cornelia Müller. And so when you have a sequence from an event sensor, we have built low-level algorithms that local motion. As you can see from a sequence on the left, you see on the right time slice images where you see different colors that represent the movement, the normal movement, what we would call the normal flow, a component of the flow on the in the image. And it is these ones that we're going to utilize, these kinds of images. And we will associate with them the movement from data that we'll be collecting. So we have drones that move, and we have knowledge of the ground truth movement by measuring it in a different way. And now what we have to do is represent in hyperdimensional space some real number quantities So for example, if you have a range, you can pick two random hypervectors to represent the two ends. And then you can keep changing one to reach the other. And that way you can have some resolution, whatever that resolution is that you want to cover between X and Y. So you represent all the numbers in between. Okay, so here's a heat map for the encodings. Now the images we represent with these permutations of rows and columns, as you see here. And then the ultimate thing of the image is the exclusive OR of all the pixels, so to speak, which are in this case events. So the state of the art in this problem, because we use data sets from self-driving cars data sets. So the state of the art is CNN deep learning give you 7 centimeters per second accuracy. And this approach gives 9 centimeters per second accuracy, but you have 270 times compression. And it is extremely cheap. So here is a pipeline. You collect the images, you create these time images, which then you transform into a hyperdimensional vector, and then to that hyperdimensional vector, you associate the particular movement. So if you have velocity in X, Y, Z, so let's say we consider the X velocity here. So you have a number. And so you create hundreds of velocity bins that are represented as hypervectors. You collect time images corresponding to each one of these bins, different values, and then you form memories. Those memories are those corresponding images and taking the exclusive or the binding with a particular value, and so on. This is the memory you are building. And so now, when you have a new input, what you do is you are doing this operation, and you choose the result that is close to 0. That's your answer. Very simple. So here's the results where you track the velocity, the two colors. It works very well. Here is from different data sets. And at the bottom here, there are indices of how well you are doing. So the technique is very close to the state of the art, but basically it compresses a neural model to a handful of 8K fit vectors. The training time is minimal. You have massive speed up of inference time, no need for expensive hardware, and requires a fraction of training data for optimal performance. And of course, we have figured out ways of taking different coding techniques. These are coding techniques where you take the image and you turn it to a hypervector. And we are combining them to get much better accuracy. Okay? So, as I was saying before, that's the algorithm here. So basically from examples, you have learned all these hypervectors. Yes? And then you bind them with a particular value of the velocity, and the matching that you get is going to be what you are looking for. So, summarize the memories that we have, like you went to the supermarket with work. You just don't remember all the images, remember how you were moving as well. So the memories are the multiplication, so to speak, of time, of vision, with motor, and the other sets. So using hyperdimensional computing, we are trying to redo computer vision and robotics. from the ground up, where basically have an image, and the image contains a number of objects at different locations. You can write the image as x1, which is the hypervector denoting the location of the first object, times O1, which is the content, a little window containing the object, plus x2 times O2, etc. Now the problem of segmentation is from that sum to get the individual components out. Thirdly, our collaborators in the Bruno Olhausen lab, they have developed a network that they call the resonator network that is able to decompose a product. If you have a number of hypervectors that are multiplied, under some conditions you can find its individual one. So, here dog, here grab. If you hear the word dog or you see the word dog, it all goes to the same hypervector. And the problem, the biggest problem in intelligent systems is the integration. How are you going to integrate this with that? Something that is always an afterthought. Hey, you are doing control and planning. Let's combine your stuff with my stuff. We integrate it. $1 million project. It's an afterthought because we are going to combine what you have already made. What if it's not good? What if it's not the right one? You have to start from the beginning. And using these hypervectors passes the integration problem. There is no integration problem any longer because everything is a hypervector. The language has been established. And so this gives you another view on AI and intelligence that is on the diametric side of the super intelligent, better than human, trillion, all kinds of problems. If you have a system that has basic visual capabilities, it can move, avoid obstacles, understand how it's moving, find its home, land, take off, and do this navigation tasks. And an episodic memory, what you saw today, a semantic memory, the knowledge you have about objects, visual memory, the knowledge you have about fluid tasks, then what you have is a cognitive system. System that is able to use its capabilities in order to interface with those memories. It's a cognitive system. Through that minimal cognitive system, we can understand intelligence in a much more short manner. Last, we can expand this minimal system.
Great thought-provoking presentation. Any questions, John?
So in any computing system, what you call memory, what you call processor? Everything. You will come to a point where
You know, in traditional AI, there is the so-called curse of dimensionality. To say, oh, too many dimensions, oh God, we have to reduce, we have to reduce. We are not saying that. No, we want these dimensions. We want this space, because this space has amazing properties. So
But there has to be a.
oh, okay, yes, these are very good questions. There are partial answers. The never has a recent paper.
Because I mean, when
on
we
this
study,
study. Yes, you're right. There are limits.
when things reduce.
Not forget it, yes.
It's enough.
Not yet. But the consolidation of knowledge when you speak, you have learned new things, you have put them in this type of thing. Fast, now that you sleep and you're doing nothing, you can do some rearrangement of that space. So that open question.
Go ahead, John.
Oh, learning happens by constructing an appropriate memory. Constructing an appropriate memory, and then when you have to solve the problem, you have to go and match into the memory, and the memory will tell you what the action is. You can do both supervised and unsupervised. Also, you know, I spoke about tasks that can be modeled by interfacing. Also, you think creating those hypervectors. Model that takes some input and learns how to put out.
Great. I'm going to propose, in the interest of time, that we break now for the last break of the symposium. If you have more questions, feel free to stick around and ask more questions. Let's thank the speakers one more time.